All right. Now that it's already 11 o'clock, we can continue with our discussion regarding predictive coding. So it may be a good time to put that title here, which is predictive coding. So what is this one about? It's about um, reducing the energy of the input signal or entropy of the input signal, which are equivalent terms to one another, so that in the rest of the stages where maybe a quantization may work, or without the quantization, some lossless coders may work even more efficiently. But how do we reduce the entropy, or how do we reduce the energy of the signal using predictive coding? We can think of this as an example. Suppose that we have a signal that is gradually increasing in value in discrete time, like this. Um, the dynamic range of the samples of x of n may start from some very small value, and then it may proceed all the way up to some very large values. So it means that we need um, a lot of energy for their representations. We need a lot of symbols, first of all. By the way, as you see, every value within this range appears only once, for instance, for the signal. Therefore, we cannot really think of a way of Huffman coding, for instance, to encode it in an efficient way, because the distribution is very uniform. So how can we increase or improve the compressibility of this? What we can do is, for instance, we can focus here a little bit and measure this incremental amount. I may use something thinner here, like this. Okay, so this amount may be our additional prediction, which we can say D, for instance. Now let's come back. And then we can say that for every xn plus 1 as a prediction, I can say that it is essentially xn plus D. So this may be my prediction, or another alternative of x hat of n plus 1, which is not equally efficient because it's not predicting very well, but it is still a prediction, could be x of n itself. So let's think of this one as our prediction, because making a prediction of xn plus d is a little bit too smart for our purposes, let's say. So xn plus 1 hat, which is the prediction, is equal to x of n, the previous value. Then every time we make a representation, we have a new sequence of y of n, which is the real value of x of n minus its prediction. Okay, this is our new sequence. So y of n, if we just convert x of n into y of n, it's going to look like this. The first sample will be itself, because previously it was 0, and the difference between 0 and itself is itself. But then the differences will be only d, because the one with the previous sample, the difference between the actual and the previous samples is always d. So it will be d, 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 etc. So from this one to this one, the prediction makes a change in the signal, in the input signal. Previously it was x of n, now we have y of n. And this new y of n is significantly lower energy signal. and we will measure in two ways. We will either take a look at the entropy of the outcome or the energy of the outcome, which will be noted by the variance. So you may take a look at the variance of the signal. So this is not x anymore. And the variance of this signal, which one is lower? The lower one will be preferable, and we will make a success measurement in terms of the variances only. Of course, they require their own compressors, representations, and you may not really achieve an efficiency from this value down to this value. So your compression efficiency may not improve like that, but it will be related to that. It will be comparable between this and this. So by predictive coding, what we are going to do is we are going to try to make a prediction of the next sample by taking a look at the past samples. It doesn't have to be taking a look at only the most recent sample. It may be more than that, essentially. And as a result, this y of n signal will be our prediction error. And that is the sequence that we will try to compress or represent. Now, there are two ways to approach to this predictive coding problem. We will be dealing with the second variant mostly, but we will start with the first one, which is in terms of a Markov chain way of looking at things, and looking at the entropy, just the probability distributions, in other words. Like this. The other one is, which is more towards the signals, and it will show us the reduction from sigma x squared to sigma y squared. And for this one, we will be using linear predictors mostly, because nonlinear predictors are difficult to optimize, but they perform, of course, usually better. So construction of a linear predictor is a science, and since this is a scientific course, we will be learning that one. But the nonlinear predictor is usually an art. It's like being smart enough to see what kind of predictions we can make and what kind of nonlinearities we can exploit. But we will be dealing in this course with linear predictors. And the majority of the course will consist of linear prediction. The majority of this chapter will be regarding linear prediction. Because its optimization is quite technical and doable. Now let's continue with the first method. Let me put it like this. In the first method, we will be making some assumptions, or we will be trying to measure the probability dependence. So what is the probability mass function, PMF, of x of n given all the past samples, n minus 1, x of n minus 2, x of n minus 3, all the way until indefinitely past. If this is equal to, I will put an if here, if that one is equal to probability mass function of x of n given a finite set, x of n minus 1, x of n minus 2, x of n minus 3, up to, let's say, x of n minus k, a finite past crop. You crop only past k samples. are contributing to the probability mass function of the current sample. We are using only K samples. Then we can, if this equality holds, then we can say that we have a kind of a Markov K structure, which is in the form of a chain structure essentially, but chain structure is mostly visible if the probability mass function depends on only the previous one. X of n probability mass function depends on only probability of x of n minus 1. Then it more looks like a chain. Then it becomes something like this. If k is equal to 1, then we have this kind of a situation. We have so-called states, S1, S2, S3. These states are S4, etc. These states are like not the symbols or bytes or the alphabet that we're talking about. They are intrinsic states, and the outputs are generated while something is making a transition from one state to another state. For example, from state 1 to state 2, if a transition occurs, then we emit an output from, if the current state is S1 and the next state is also S1, we emit another output. If from S2 to S2, we emit another output if the transition is like this, or from S2 to S3, from S3 to S4, S4 to whatever. It may be coming from other places. It may be a very long set of states. We may have a loops, so the next state may stay the same, or it may be to the next state or to the previous state. So it's like this. The situation of the Markov chain is like this. If we can make a model like this, then the entropy of this kind of a model becomes significantly lower than the entropy of the row structure without this kind of a model. It essentially becomes like this. So the entropy H becomes, depending on how many different transition outcomes may occur, let's call it M, it will be probability of each state times entropy corresponding to each state. And this can be seen that it can be seen that this is quite an optimal way of doing things. But if we just write it like this, it becomes too much abstract. What are we talking about? What are these states? What can we say about practical application of this to, let's say, a predictive kind of coding? And I agree with that. Therefore, I will start by showing an example of a binary image. If the binary image is compressed using, let's say, Huffman coding, and if half of the pixels are black and half of the pixels are white, just two values, then the probability of black will be 1/2, the probability of white will be 1/2, and the entropy that is necessary, or the bit rate that is necessary to make a representation per pixel will be 1 bit per pixel, right? 1 bit. If it is 0, it is black. If it is 1, it is white, for example. We cannot use less than 1 bit. But if we use the formalism of Markov chains, we can see that there must be ways, we don't know what that way is yet, but there can be ways to represent this binary image with less than 1 bit per pixel. And how do we do that? So the binary image Markov model is actually like this. We have a black state and a white state, and this happens with the probability of transition from black to white. This happens the probability of transition from white to black. This is the probability of white to white, and this shows the probability of black to black. Okay, so we have a very small two-state Markov chain for the binary image case. Now let's try to evaluate or calculate the entropy of this overall system using this strategy or using this expression. What is the entropy of the black pixel? What is the entropy of the white pixel? And what is the probability of black and white pixels? Is something that we have to calculate. And here, the entropy of the black pixel comes out to be probability of white to black, this one, times logarithm of probability of white to black, because by the way, I have to put a minus sign, sorry about this. I'm writing the entropy definition with a probability times logarithm probability with a minus sign, because this probability would correspond to the transition from white to black, so the new pixel becomes black. It can appear or occur like this, or it can be black to black. So if the previous pixel was white, we have this expression. If the previous pixel was black, we have this expression. And the combination of that would give me an entropy for the black sample, HB. Similarly, the white pixel entropy is negative of probability from black to white logarithm from the probability from black to white minus probability white to white logarithm probability white to white. Okay, and the overall entropy that we can then calculate is probability of black, which needs to be calculated because as you see here, we don't really have probability of black. We have probability from black to white, from white to black, white to white, black to black. But we don't have probability of black, and we don't have probability of white either. They need to be calculated, and we have to see that. And I'm pretty much sure that these Markov chain steady-state probabilities and etc. Are you may already know about these things. This probability of white, entropy of white. This scaled summation, accumulation, will give you the overall entropy. And this overall entropy is actually smaller than, in general, smaller than or equal to, let's say, the case where the probability of black is 1/2 and entropy of black is 1, and probability of white is 1/2 and entropy of white is also 1. So 1/2 times 1 plus 1/2 times 1 will give you 1, but that is the maximum case. That it may be, the thing may be less than that one. And please notice that these probabilities are not arbitrary. If you are given some of them, you can actually deduce the others. For example, probability of white to white is essentially 1 minus probability of white to black, because from white it will either go to white again or to black. And similarly, probability black to black is equal to 1 minus probability from black to white, right? We know these things. Now, using this kind of a strategy, it's possible to solve some problems, and we will see the example, a numerical example here as well. But before that, let us let me show you how to calculate probability of black and probability of white if they are not given to you, but only these probability white, white, black, white, etc. These are given to you. Probability of black, probability of white vector, this probability vector can be constructed from like this. Probability white to black, probability, excuse me, the first one is black to black, white to black, probability of black to white, probability of white to white, times probability of black, probability of white. What did I write here? I was constructing the formula meanwhile trying to write it. That's why I didn't explain. Now we can explain it. The cumulative probability of black is achieved by multiplying this row with this column, which corresponds to the probability of black to black times probability of black. So it was black, and with a probability of black to black, it again stays black. Plus, it was white with a probability of white times probability white to black. So it converts to black. So this row times this column will give you this probability of black. It must give you. And similarly, probability of black to white times probability of black will give you a contribution to be converted to white. And probability of white to white with the previous probability of white multiplication will be again producing a white pixel. So multiplication of this row and this column will give you probability of white. Now here there are two unknowns which we are not given, let's say, which is probability of black and white here, and these are given to you. Then you must insert that matrix, write this equation, and solve for probability of black and probability of white. It will give you two equations with two unknowns, and probability of black and white must be evaluated from this steady state transition matrix. This is called the Markov transition matrix, by the way. Markov transition matrix. And using this transition matrix and assuming that after the transition, the probabilities will remain the same because in the steady state, the probabilities don't change. We apply it to probability of black and white, and we obtain, again, probability of black and white. So we have to solve for this. And obtain probability of black and probability of white. So this is how we normally find probability of black and white. But in the numerical example, let me also say it again an example, although the previous one was not really an example because it was not numerical, it was just a case of Markov chain 1, Markov 1 for black and white images. This example is a numerical example. We need to calculate the entropy of the source, of a binary source, using simple probability model and then using Markov model. Markov model. So you will see the difference between these two. The given information is as follows. We are given the probability of white. So we are not given the transition probabilities. We are also given the standalone probabilities, which may not be compatible with the expression that I gave you here. But this is just an example, okay? Normally, probability of white and probability of black wouldn't be given to you. Only the transition probabilities are given. But for this one, let's assume that they can be found like this. I didn't really check whether they are correct or not. So probability of white is 30 over 31, which means a majority of the pixels are white. It may be like this textual image that you see on the screen. A majority is consisting of the background white paper background, and therefore the probability of black will automatically become 1 over 31. So only a few black pixels are there. It's like this drawing that you see on the screen. But maybe the more important ones are probability of white to white is 0.99 and probability of black to black is 0.7. Now you may be a little bit surprised about these figures. You may not be surprised about probability of white to white to be such a high number, because if a pixel is in the background, probably its neighbor is also in the background. So there's a 0.99 probability that we will again see another white pixel. But it is surprising to see that probability of black to black is also somewhat high, 0.7. Why? It's because of this. If you zoom in these pixels, as you see, the black pixels that you see over there will have a neighbor which is also a black pixel, and its neighbor is also a black pixel. So probably if you encounter a black pixel, its neighbor will also be black. Although they are few, they are also in terms of clusters. So black pixels are also clustered. That's why actually it makes sense to have probability of black to black to have a figure like 0.7. So using these, first let me tell you what is the answer to part A of this question. Simple probability model. It is entropy is equal to minus probability of white logarithm base 2 of, sorry, the denominator is 31, sorry. Logarithm of 30 over 31, the probability of white in other words, minus 1 over 31 logarithm base 2 of 1 over 31. And this one, of course, you cannot do just by paper. You have to use calculators. And when you use calculators, as far as I can reckon, it's something like 0.2 bits per pixel. By the way, this is also quite small. It's not 1. It's 0.2 bits per pixel. So even this entropy is giving us hints that using 1 bit per pixel for this black and white image is essentially redundant. We should be able to find way more efficient ways of compressing the data in such a way that it reduces 5 times. But even this one is larger than the entropy that we will find using the Markov model, because for the Markov model, we have to first find the entropy corresponding to the black and then to the white pixels separately. And the entropy of the black pixel is from white to black. What is white to black? We can evaluate from here. We are given probability white to white, and 1 minus probability of white to white will give you probability white to black. So we must have this 0. Minus 0.01, which is from white to black, logarithm 0.01, and minus from white to white, which is 0.7, I guess, logarithm 0.7. We must first calculate this one, and then probability of white, which must be from black to white, the probability of black to white is 1 minus probability black to black, which is 0.3 minus 0.3 logarithm 0.3. And then I must have probability white to white, which is 0.99 logarithm 0.99. And these must be evaluated. The only bad contributing situation appears, well, it appears from 0.7 and 0.3. They are the largest contributors. But unfortunately, I didn't take note of these values in my notes, unfortunately. So let's continue and give it as an exercise for you to help me to come back to this note and try to evaluate what these are. Or if you have some computer related things, please give me the results, because I don't have the results now. What is the first HB, the entropy of the black pixel, and what is the entropy of the white pixel? Please do not forget to evaluate the logarithm in base 2, okay? You don't have to do it right now. You can do it later in the next week. You can tell me the answers so that I can write the answers here. And therefore, from these two, I can evaluate the overall entropy as probability of white times entropy of white plus probability of black times entropy of black, which is probability of white is already given as 0.99. H of white is something, plus probability of black is given as 0.01 times, uh, no, it's not 0.99. I'm just messing up. Excuse me, I'm erasing this. Probability of white is 30 over 31. Excuse me about that. Wasn't it? Yes, it was 30 over 31. So it's not necessarily 0.99, but it's similar to that one anyway. Times HW, which is something, plus 1 over 31 times the entropy of the black, which is HB.
Professor,
Yeah,
the logarithm there, the logarithm
yes.
is based on two.
Mm-hmm. Yes, the
Oh,
logarithms are all based with 2, of course.
okay, thanks.
Yeah, yeah. This one and this one, of course. These are entropy definitions, so we are definitely using the logarithm 2 base. And this, according to my notes, but I didn't check them, and I'm not sure about their validity, but it's like 0.107 from my notes, which I suspect a little bit. But let's assume that these are the numbers that you get. And if you see it that way, then you make a comparison between the standalone entropy and uh, incremental or transitional entropy. They are quite different. It's almost twice more efficient if you use the Markov model. So part A of the question shows us that you can find standalone individual representation methods, like you may combine the figures all together, and these combined things may be represented using 0.2 bits per symbol overall efficiency. But if you use the transitions like run length kind of an approach, or a predictive kind of an approach, then you can even reduce the size even further to 0.1 bits per pixel. Now, as I say, I didn't check the numerical values and they may be inaccurate, but this is the general idea. That's what all I would like to say. This also gives us a hint about the so-called, so the examples ends there, about the conditional entropy. There is a concept called conditional entropy, not the entropy of x, but entropy of x if y is given. This y can be a different signal, or it can be the past samples of the same signal. Okay, and that is equal to this kind of a summation. Let's say we have and symbols. Probability of xi given y and logarithm base 2 of probability of xi given y. Normally, if I evaluate entropy of x as h of x, this given conditional probabilities wouldn't appear here, of course. And when they appear, we come up with a very nice observation which can be proven, and the proof can again be an exam, a take-home exam question like this. Conditional entropy is always less than or equal to the mutual entropy. The proof of this one can be done by you, but it uses the so-called Jensen's inequality. The Jensen's inequality is a useful inequality that can be used in several proofs regarding the concave down functions. So the linear functions versus concave down functions, when their orders are interchanged, we come up with an inequality. If the linear operator is performed on the concave down function of a probability density function of another function, f of x is just a function here. So we apply a concave down function to that and then take the expected operator, which is a linear operator. This thing is always less than or equal to first applying the linear operation and then applying the concave down function. Logarithm base 2, for example, is the concave down function. And inside it, we first apply the expectation operator like this. This is called Jensen's inequality. You can use it. You can even try to prove this one. Its proof is also, it can be found on the internet or something. But using this, the entropy, conditional entropy inequality it can be proven. So using this Jensen's inequality, you can prove it. The proof uses that one. Maybe I can ask this as an exam question in the take-home, as usual. And the mutual information, there is so-called the mutual information that is the thing that is usually compressed, okay, the residual thing that you have for compression purposes, and that is, excuse me, notated by I of x semicolon y. So this is the mutual information among x and y, is given as the entropy of x minus the conditional entropy of x given y. That amount gives you the mutual information of two random signals x and y. Now, this was an approach of predictive coding in the sense of entropy and probabilities and such, which is something that we will not really do in our predictive encoders, because they are in the form of probability and they do not provide us anything related to what is then the prediction, what is the x hat of n then, because we need to find it. X hat of n needs to be determined for the compression. And the thing that will give us x hat of n is a topic related to linear prediction. As you may remember, it was part 2 of the predictive coding scheme. So now we will continue with the part 2, and in practice, we will be using this linear prediction. The linear prediction has this kind of an idea. It assumes the so-called autoregressive AR model. An autoregressive model is like this. It is claiming that the current or the next sample in a time series is determined by linearly combining the past samples within a window, not indefinitely. Otherwise, it would correspond to AR infinity model, but normal AR models just use finitely many past samples and linearly combine them. And there is an uncertainty amount, which is just independent from the input. So it is independent additive noise-like figure that needs to be incorporated. So the AR model is this: x of n is assumed to be modeled as a summation, let's say from 1 to n, a linear combination, ai xn minus I. So this linear combination combines the past samples by scaling them differently with AI, with the corresponding AI, and then make a linear combination. That is an autoregressive model. And plus there is a noise, epsilon of n. This noise is the independent noise, which cannot be predicted. And that is the noise that we will try to compress further. It will have smaller variance. It will have smaller energy. The variation of epsilon will be significantly less than the variation of x of n if you can make a successful prediction. So this is the prediction error. Prediction error. This AR model is a good model for us, and we will continue from there. But normally, linear models are not limited to AR models. They can be, but I will just draw them in a different color. In general, a linear model is autoregressive as well as moving average, ARMA. This kind of shortcut terminology is, I'm sure you have encountered. It's something that you have encountered, an ARMA model. What is an ARMA model? It contains an autoregressive part as well as a moving average part. But that moving average part has nothing to do with prediction because it uses future samples. That's why we will not be dealing with the future values, and we will not be dealing with moving average models in linear prediction. But nevertheless, just to remember that, let me write that one too. X of n is essentially the autoregressive part, the same, ai x n minus I, plus a moving average, which is filtering this time the noise error because it is related to the future samples. So I can write it like this: j from 1 to m. So the autoregressive and moving average window lengths could also be different. A filtered noise plus the model error, which is epsilon. As I say, we will not be dealing with the ARMA model. We will be dealing with the autoregressive model only because it has a nice way of making a prediction in the form of filtering the past samples only, not dealing with the noise accumulation or whatever. So our future goal will be um, determination of these coefficients, because we will be linearly combining the past samples. What are those linear multiplication coefficients or scales that we will be using? Once we have that scale, it means that we discovered our predictive filter, linear filter. Because as you see, this part is essentially a filter. And that filter is using filtering the past samples in a sliding window manner. And each time it produces an x of n. So this will be our prediction. This part will be the prediction. And as you see, this part will be the prediction error then. But the prediction requires the determination or the knowledge of AI. So how can we find these AIs? Now, how much time do we have? We have about 13 minutes or something. I will only write down the formulation, the equation of the thing that we want to minimize. Clearly, we want to minimize the prediction error, but I'm not going to show you how to solve it, which is the more critical thing. We will continue with that one in the next week. So in linear prediction, x hat of n is quite simply I from 1 to n. I will say hi x n minus I. Previously, I was using AI, but it's the same. I'm using H here because I want to emphasize that it's actually a filter. So these are HI are the filter coefficients. And then we will have a difference d of n, which is the prediction error that can be considered as, it can be considered in two ways, but I will use x n minus x hat of n, or you can use x hat of n minus x of n. It doesn't really matter. So this is the prediction error, and we want to minimize the expectation of d squared of n, which is the power of the prediction error. And we will see that when we do the optimization, can it be linear or nonlinear prediction, no matter which one you choose, the prediction error expected value must be 0. So expected value of d of n needs to be 0. Otherwise, it means that you are making a biased estimation, biased prediction. And for example, if d of n is positive, it means that your prediction is persistently less than the actual value. It's a biased prediction. But a biased prediction cannot be an optimal prediction. The optimal prediction must have a 0 average. So mean of d is 0, which means that this is essentially equal to the variance of the prediction error. As I say, this is because mu of d must be equal to 0. We will write down these equations and show that it must be 0. It can be proven with the probability or random process things that we have seen in the beginning of today's lecture. Using those strategies, we will show that the minimization of the variance will give you the optimal filter. We will start next week by the first order prediction filter, which is quite an easy one. So the case one will be x hat of n will be equal to h1 x of n minus 1 only. So the summation, capital N, is equal to 1. We are using only the previous sample. So what is the optimal value of H1? We will first discover this one. Then we will extend the example to second order, like x hat of n is equal to H1 x n minus 1 plus H2 x n minus 2. That's a second order system. We will also deliberately solve that by minimizing the variance of the prediction error. The prediction error is the difference between xn and x hat of n, and it has an energy. We will evaluate its energy. the expected value of the energy. And we will come up with solutions for optimum H1 and H2, etc. And then, of course, we will have to generalize everything to, if it's not first order or second order, it may be quite long order. Is there a better way of making a representation of that long order linear prediction filter? How can we find the coefficients of that longer filter? And we will see that it's pretty much easy. And we will continue that way. And then we will see mathematical methods to solve that equation. We will see, can we really quantize the prediction error? Because if we quantize this prediction, this prediction error here, this one, then the quantized version of that will not help us to perfectly discover x of n. And since we don't find the exact value of x of n, we cannot use it for the evaluation of x of n plus 1 in the next iteration step, and the errors will grow, accumulate, and diverge maybe. So we have to incorporate the quantization into the prediction system, which is also known as differential pulse code modulation, DPCM, differential pulse code modulation. We have all those issues related to predictive coding, but prediction is astonishing, and it's a very useful tool, not only for compression purposes. It helps us to compress. By the way, if you're asking for real life applications of PCM, DPCM coding, well, DPCM is essentially used in voice communication mostly. Speech coding, speech compression. It uses a lot of predictive coding inside. Videos, etc. They don't. They use a different way of making prediction. That time they make motion predictions. What is the motion of this shape in the next frame? In the first frame it was here. In the next frame it is here, and the next frame it is here. So there is a motion from here to here. So we will be using that kind of a prediction, which is again in the broad concept of prediction. So prediction is an important thing. It's also important in other disciplines, like, I don't know, maybe in renewable energy systems, for example, because we want to predict what will come as the wind speed 1 hour later. So because accordingly we will put a price tag on the wind energy that we are going to sell using our wind turbines, or yeah. So the capacity, knowledge of the capacity of the future, it may be solar radiation. We want to predict. It may be the consumption of electricity that we want to predict from using past samples. In the future, what will be the consumption, electricity consumption? Without that consumption prediction, how can we satisfy the electricity demands of the users? So the examples can be enlarged. Prediction is important in all aspects, as well as compression, and we will be dealing with the compression aspect of probable of prediction in this throughout this course. But I'm sure that even if you may not be working on signal compression, you will find it useful, this prediction concept. So this concludes today's lecture. I'm going to stop the recording. But before that, maybe I can ask you if you have any questions. If it's understood, clear, we will continue. We didn't really do a lot of fancy things today. We just made an introduction, so maybe you don't have much questions, but let me ask if you have any questions. Even if you have no questions, please say, no, I don't have a question.
No, thanks, Professor.
All right.
Thank you, sir.
All right, then. So I can stop the recording then and stop the meeting as well. We will meet next week, the same hour, 9:30. Okay. See you.
Okay.
Goodbye.
Have a nice week.
Thanks.